we will start recording. All right. Okay, so can you guys see my screen now? Is it okay?
Yes, okay.
All right, thank you. Okay, so before we start, everyone please write down your name together with the regional center in the chat box. Okay, so today will be our final tutorial 4 actually, but then this is actually unit 5 because in tutorial 1 we have unit 1 and 2. Okay, so this is our final unit. We have 5 units altogether in the signal and system. Alright. This is the one that we will cover for your analysis of discrete time signal. Not to the slide only, I have, I think, only 43 slides. Okay, 43 slides. Before we start, just simple reminder for you guys. Okay. The course assessment one is already behind the deadline, right? So I hope that everyone is already submit the course assessment one. I have done marking all the submitted files and these couples of day I haven't checked. I think ada lagi satu atau dua yang belum submit. So I haven't checked either the students already submitted or not. Okay, for course assessment one. And the marks will be released, I think, anytime from now, around, might be around next week. Okay, the course coordinator will release the mark. Okay, Dr. Hazri will release the mark. And then you have to submit the course assessment 2. When is the deadline? Anyone please share with me the deadline for course assessment 2?
23 on March.
23rd March. Okay. Lagi I think dalam 2 weeks lah lebih kurang. Okay. Another 2 weeks. Okay. So you need to submit the course assessment 2 before the deadline. There is no extension for course assessment 2. Okay, remember guys, no extension for course assessment 2. And what is the course assessment 2? Okay, sebelum ni ada my students yang tak tahu what is course assessment 1, what is course assessment 2. And I'm a bit surprised lah. So because I think I selalu mention and explain dalam class before we start with the slides, I always mention on the simple reminder lah when you need to submit, what you need to submit and so on. Okay. So course assessment 2 is basically on the simulation experiment that we have conducted I think around 2 weeks ago macam tu. Okay. On the course assessment tu on the what we have conducted using the Simulab. Apa yang kita pakai? What else? Aku dah lupa. Okay. So for those who haven't completed on the simulation, please do the simulation and put it nicely in a report for your course assessment 2. That will be your course assessment 2, carry 30%. Your carry mark will be 30% course assessment 1 and 30% course assessment 2. And your final exam will be 40%. Okay, in the OAS, kat mana nak submit? Ada yang tanya. In the OAS, you need to submit the course assessment 2 before the deadline 23rd March. Okay, and the course assessment 3 or the final exam, it is the same thing. Course assessment 3 and the final exam. Okay, the question is not available in the FlexLearn because it is online final exam, real time, meaning that during the scheduled time, the allocated assigned time, not me who will be conducted on the invigilate for the final exam, the unit exam, staff from our side will conduct the session. Okay, they will release the question for final exam or the course assessment 3. Okay, if in the OAS, it is the course assessment 3 lah. Okay, they release just about the time. Okay, and you will only be allocated, I think, around 2 or 3 hours. Saya tak pasti that one. Okay, and where to get all the information, you need to keep updated in the FlexLearn or in the student portal. Supposed to be all the information akan di share in the all the available portals lah. But also you may ask straight away with the course coordinator, the Dr. Hazri. Okay, because all of that direct from the unit exam dengan Dr. Hazri. Okay, with me, as for me, tarikh pun saya tak tahu lagi bila on the final exam. Okay, so please everyone keep updated on that. And one more thing, the final exam will be during weekdays. Okay, biasanya lah. And if you need to apply leave at your workstation, workplace, then you must apply for the leave lah. If because normally if you cannot apply for whole day, then you can apply for half day. And you need to have very strong internet connection during the session. Normally they will medium or platform, they will use the Microsoft Teams too, and then you need to turn on your camera during the session. Okay, sebenarnya sama as previous semester lah. Okay, that is for final exam. And final exam you need to submit straight away. Okay, all the questions for final exam. You don't have to type everything. If for calculation or any sketching, then you can hand sketching je. For calculations pun, you can straight away handwriting sahaja. Screenshot and then paste in Word. Okay, barulah you apply, you upload in the OAS system. Alright. Okay. So that's for course assessment 1, course assessment 2, and the final exam. Okay. So back to our lesson today. It is on Fourier analysis of discrete-time signal. Any questions on the final exam or the course assessment, guys? Before we go to Unit 5.
No, miss.
Alright, good. Thank you. Okay. So Unit 5 is on Fourier analysis. Okay. This is a very important section or topic in signal and system or signal analysis. For those who are always dealing with the signal analysis or signal processing, or in your final year project, in Wawasan, they call it as a EL project. If you want to do some a project on the signals, then you will dealing with the Fourier analysis. Okay. In the case of continuous time signal, independent variable, or usually we call it as a time, t, is continuous. On the other hand, discrete time signals are defined only at discrete point in time, and hence the independent variable takes an only at discrete set of values. And it is important to note that the discrete time signal, or we call it as the XM, if it is discrete, if the function is Xn, okay, this is in discrete. Okay. Oh. Okay. If xt, it is in continuous signal. It is important to note that the discrete time signal is defined only for integer value of the independent variables n. Okay, and we may wonder why we have to work with discrete time signal when continuous time signal are more common. Normally, when we have signals or we take the data, it is in continuous time. Okay, the answer is very simple because of the computers. All the programming, all the tools that we are using is the computers, and all the analysis it is in discrete. Okay, it is basically in discrete analysis. Okay, for these digital machines is capable of processing huge amount of data rapidly, and the proliferations of computers has led to many other things becoming digital too, like the televisions and other smart screens. Computers unfortunately operate only in discrete time domain. Thus, to be able to efficiently process signals using computers, these signals have to be discretized. Okay, that is why we have continuous time signals. The data we convert into discrete. The xt we convert into xn. Okay. Okay, so this is our topics for today. Frequency domain, Basically, in normally you have already familiar with the time domain. Okay, we can do the conversions from time domain to frequency domain or frequency domain to time domain. And also we have the 1D Fourier transform, 2D Fourier transform, and the properties of the Fourier transform. Okay. So now we go to frequency domain. Okay, what is actually the frequency domain? And um, if we look into the image processing, okay, where we can apply. Okay. The frequency domain refers to the analysis of mathematical functions or signals with respect to the frequency. Normally in frequency domain, we do analysis in the frequency. Okay. But then if we have the data, for example, if I believe that you guys very familiar with the ECG, okay, electrocardiogram, the heartbeat. Okay, the signals normally macam ni lah kalau dekat doktor tu. Okay. And this is ECG. We if ataupun ECG is for heartbeat, heart rate. It is in real time data. Okay, and then it is in time domain. Okay. My research is basically before this I actively involved with the EEG. EEG is electroencephalogram for the mind or brainwave signal. Okay, brainwave signal. Signal dia lebih kurang like that. Okay. And this one, when we record the data, same goes with the ECG. Okay, another one, we also have the EMG. EMG is for muscle. Okay, ECG is for cardio. This is for electroencephalogram, the brain, and then this is for muscle. Okay. The signal, the doctors record the signal in real-time data in time domain. Okay, but then all the medical practitioners, they do not do the analysis because in order to do analysis, we need to convert into the frequency domain. Okay, we convert into frequency domain. We use what? We use fast Fourier transform, FFT. Okay, and all the analysis we apply in the frequency domain. Analysis, well, we want to use MATLAB ke, we want to use, this is another tools lah, SPSS ke, okay. And who do the analysis? Okay, normally engineers, data analytics do the analysis. Okay, the doctors only record the data. The doctors or the researchers lah, they record the data. And then we do the analysis in MATLAB, SPSS by applying some of the FFT and few other methods yang kita apply lagi lah. Okay. And all the analysis we do is in frequency domain. Okay. And if the time domain, the signal, okay, like this lah. Kalau the signal, okay, uh, this is the time in second. Okay, this is normally amplitude. Amplitude in terms of the power, the voltage, depends. Okay, and then we need to convert in order to do further analysis or further modeling. We need to convert into frequency domain. Okay, for frequency domain, this is will be hertz lah, because it is frequency. Okay, and then in the frequency, it is will be discrete. So the signals, okay, because it is discrete, depends lah. Okay, this frequency domain will carry exactly the same information as in the time domain. Okay, the information must be sama. Kalau tak sama, how we can do the analysis? Okay, so informations mesti sama. So that the characteristic that we do, analysis that we do in the frequency domain, we can reflect with the data that we recorded in the time domain. Okay, so ini adalah some brief connections in between the time domain and frequency domain. Okay, the frequency domain refers to the representation of signals in terms of their frequency components rather than time, and important in image processing and signal analysis to understand how different frequency components contribute to the signal. Okay, alright. So Fourier series we go to the background of the Fourier series. Any periodic function can be expressed as sum of sines or cosine of different frequencies and amplitude. Some of the subject in mathematics or numerical methods, we also introduce the Fourier series. I have teach numerical methods with applications before this in my university. In the syllabus, we have the Fourier series and Maclaurin series, okay, chapter 1. So this one also you may find this in some subjects related with the mathematics. Frequency domain interpretations, the final signal contains multiple frequency components which can be analyzed using the Fourier transform. And for signal composition, the more frequency components we add, the more complex or resulting wave form that we can obtain. Okay? Um, Fourier transform non-periodic functions can be expressed as an integral of sine and cosine multiplied by what we have the weighting factor lah in the formula. Extend for this idea to non-periodic functions, representing them as an integral of sine and cosine wave. Okay, this is contoh for the signals with different frequency. In Fourier series representations, any periodic signal can be represented as a sum of sinusoidal with different frequency and amplitude. Okay, we have three different signals here. Let's say this is A1, the signal 1, this is A2, this is A3. Okay, so this all A1, A2, this is frequency, this is amplitude lah. Amplitude, sometimes in terms of voltage or power. Okay, and this one will be the x-axis will be the uh x-axis will be the time here. Okay, and this one for the first A1 is sinusoidal, A2 is also sinusoidal with different frequency. Okay, different frequency and different amplitude here we have. Okay, the highest frequency, A1 has the highest frequency because it has the smallest wavelength. Okay, and this is A2. A2 has the medium frequency, and A3 has the lowest frequency with the largest wavelength. Okay, A3. And then this is the combination of A1 plus A2 plus A3. And this one we call it as the complex signal. This is combinations of sinusoidals, more complex waveforms showing how individual frequency components interact. Okay, because we have different amplitude and different frequency for all three, A1, A2, and A3. Okay, and this is the illustrations concept of Fourier synthesis where different sinusoidal signals are combined to form a complex waveform. So this one, it is we are not calling this one as a sinusoidal signal, okay, because it is more complex, okay, in complex form. The Fourier transform is used to analyze signals in frequency domain, making it is useful in signal processing, image processing, and also for the communications. Functions, this can be recovered completely via an inverse process. We can inverse the process from frequency domain goes to time domain, and from time domain goes to frequency domain. Okay, without losing any information. Okay, we can maintain all the information from time domain to frequency domain. Okay, this is time domain goes to frequency domain. And the relationship between time domain and frequency domain using the sinusoidal signals with this is amplitude. Okay, in time domain we have time, and this is the sinusoidal wave that varies over time. This one, and this is also the amplitude, okay, with the frequency in hertz. Okay, this is the frequency domain Fourier transform of the signal, and it can be converted from one domain to another. Okay, this is the complex time domain signals. Also, we can convert for the complex time domain signal, but then it is not uh, to visualize it in time domain as this one. This is a simple signal, easier to visualize and easier to read. Kiranya macam bila kita tengok, oh senang nak baca because it is simple signal. But what happen if we have complex signal like this one? Nak baca dia punya amplitude pun tak, because it is complex signal. Amplitude ambil sini ke? Or if you want to this point ke? Okay. So, for this complex signal, it is better to do the analysis in the frequency domain. Okay. And the relationship showing how a signal composed multiple sinusoidal can be represented in frequency domain. Okay. Um, we have two types of Fourier transform and Fourier series. Okay, DTFT is discrete time Fourier transform and DTFS is the discrete time Fourier series. You can apply these two to get on the transformations from time domain to the frequency domain. Okay, we have the 1D Fourier transform, 2D and discrete formulation. And also the properties we will cover on the like we have learned before this on the linearity, time shifting, frequency shifting, and also we have the different differentiation in time and also in the frequency. And also we have the time reversal or mirror and perseverance relation between the uh, nodes, okay, as the properties. Okay, first is on the dimensional 1D. Okay, 1D, Fourier transform. It converts time signals into its frequency domain representation, revealing the different frequency components present in the signal. For continuous Fourier transform and discrete Fourier transform, we have two common types. Okay, for frequency transform extract information from the signals, and also on the inverse Fourier transform construct the original function from its frequency components. If we have the Fourier transform, also we can inverse the Fourier transform. This is in a time domain. Okay, this one is in frequency domain. Okay, you will write it in U here. Okay, the relationship between 1D function, this is for 1D function in the spatial or time domain and corresponding Fourier transform in the frequency domain. Okay, for 1D here. Okay, for example, application in audio signal analysis. Okay, uh, for example, in audio, we have the musical note played on a guitar. The sound wave in time domain is continuous waveform. Okay, the sound produced by a guitar. By applying Fourier transform, we can break the complex waveform into individual frequency components. The result is a frequency spectrum where each peak corresponds to a specific musical note frequency, depend on the note and the frequency. Okay, the digital signals are discrete, so we use the discrete Fourier transform instead of the continuous Fourier transform. Okay, this is a continuous Fourier transform. This is discrete Fourier transform. Okay, the signals need to be sampled at discrete time interval. Okay, this is actually the same signal, but then when we convert, we get this one. Okay, the sampling process using discrete Fourier transform, DFT. And where applications of this? Okay, sebenarnya. The applications of DFT in audio processing, also in image processing, communication system, or dalam we apply in Wi-Fi or error detections for 4G or 5G analysis, and also in the vibration analysis. Sebenarnya ada banyak lagi. This is some of the examples of for the application. If we go further into discrete Fourier transform, okay, since this is discrete, so we can divide into Fourier X steps lah. Okay. And this is total number of steps or the sample. This is for the frequency domain representation. Okay. And this is for discrete signal. And this one to show this is from the sinusoidal component. Okay. From the sinusoidal component. And each sample contribute to the transformation. And remember, for DFT, convert the signal from time domain to frequency domain. Okay. To convert frequency domain, data, the inverse discrete, this is IDF. Okay, DFT from time domain to frequency. For IDFT is frequency domain to the time domain. Okay, so it is opposite from DFT. So here we have the imaginary unit for complex exponential function is to reconstruct the original signal fx from its frequency domain representation fu. Okay, get the fx from the fu. Just now, get the fu from the fx. Okay, and m is the total number of frequency components. Okay, so we have two equations for Fourier transform pair. Okay, this is for DFT, this is IDFT. DFT from time domain to frequency domain, IDFT from frequency domain to time domain. Okay, it breaks the signal into frequency domain components for DFT. For IDFT, reconstruct the signal from the frequency component. And for both Fu and Fx form a Fourier transform pair, meaning one can be computed from the other. We can get the information or all the data from each signal in the time domain or in frequency domain. Okay. And Euler's formula is used to express complex exponential in terms of sine and cosine, which simplifies Fourier transform calculations. Okay. In original signals, we have the sinusoidal functions. Okay. Each value of Fu in Fourier transform is computed as a sum of Fx multiplied by sine and cosine terms of various frequency. Okay, for frequency domain, Fourier transform components. Okay, so we can apply the Euler's formula for fundamental equation express a complex exponential function in terms of sine and cosine. Okay, the J yang tadi. Okay, okay. And into equation 1 for equation 1 is DFT. Refer to this one, DFT. And this for this expression show that Fourier transform consists of real part of cosine term. Okay, cosine tak ada J, and sine we have the imaginary part. Okay, so it is combination between cosine and sine. This is real number. This is the imaginary this imaginary value. Okay, and then this formula helps to analyze the frequency content of the signals. Okay, for the DFT, convert discrete time domain signal Fx to frequency domain representation Fu, and then Fu from this formula, you can say that Fu is summation of all values of Fx. Okay, because this one, even it is subtract, it can also be summation if this is negative value. Okay, so this one we call it as the summations of all fu is summation of all fx. Okay. Each value of fx is multiplied by sine and cosine of various frequencies. For sine and cosine corresponds to different frequencies. Okay. That is why we have sine and cosine. Okay. Alright, so now we go to prism. Okay, the Fourier transform act as a mathematical prism, uh, separating a function into its frequency components. A prism is a physical device that separates white lights into its constituent colors or the spectrum. Okay, if we have satu prisma. Okay. And the prism separate colors just like the Fe separates frequency components of a signal. Okay. It is decompose a complex signals into its individual frequency components. Instead of separating colors, it also separates frequencies present in the signals and helps us to analyze and characterize a function by understanding the frequency content. We need to understand on the characteristics dulu, on the behavior, only then we can do analysis kan. Okay. For the applications, okay, the Fourier transform can filter out unwanted noise in communication system. Also can compress data that, for example, we use in the JPEG for image. Okay, we have JPEG file, and also if we have audio, okay, the file will be in MP3. Okay, so we can apply this technique for this method for Fourier transform to compress the data. Okay, examines, also we can examine discrete Fourier transform for different number of points. For example, if we have um, k equals to 8, k equals to 16 to show how frequency components change it with the resolution. Okay, this one is for active duration is 8. Okay. A discrete function consists of individual data point rather than a continuous function, and the total of m data point define the total length of the duration. Okay, the t signals. Okay, now this one is k equals to 8 point. The function is non-zero for k equals to 8. Only these points contribute significantly. Okay, and the amplitude is a equals to 1, meaning that the highest value of fx, highest value is equals to 1. Okay, okay, this is for k equals to 16. Okay, same here, fx equals to 1. Okay, the active duration here is 16. Just now, active duration is 8. Okay, the wider this is the frequency response here. Okay, this is for k equals to 8. This is k equals to 16. Okay, wider pass in time with larger k results in narrower frequency spectrum. This is narrower frequency spectrum with higher k value. Time and frequency have an inverse relationship. It is actually fundamental property of the Fourier transform. Okay, for the analysis of filtering, also for the transformations, can apply on the edge detections for image compression for JPEG file example. We have the total data points here equals to M. Okay, for rectangular function, width is 2K and the amplitude is A. Okay, this is width, this is A. And this is here we have the side lobes of oscillations, but with some decay. Okay, and here this one is the main peak or the central lobes, more concentrated at the central. For the this is overall here is the for sine function in frequency domain for 2k, and it will become narrower if we increase the value. Okay, and when we analyze the images, we focus on magnitude spectrum rather than the phase. Okay, here we have the continuous signal must be converted into discrete signal for digital processing. Okay, for these samples represent value of fx at specific point, and the samples not necessarily taken at the integer value. If sampling is too sparse, it can lead to less losses of the information. Okay, and here we apply the Nyquist-Shannon theorem. It states that to accurately reconstruct a signal, we need to sample at least twice the highest frequency present in the signals. Okay, I believe that you guys familiar or heard uh, on the Nyquist-Shannon rate. Okay. The sampling in discrete Fourier transform, the FT, here we have the mth data point. Okay, and discrete data points are taken from a continuous signal. Sampling is done at a regular interval AX. Sorry, not AX. This is the changes of X, delta X, which affect the frequency domain resolution. Okay, the frequency domain values for FU, okay, follows a specific sequence sampling rate for the delta X. For the changes of delta X with the frequency resolutions, delta U are inversely related. Okay, so here is the formula for frequency resolution, 1 over m delta x. M is the data point. Okay, one example here. Sampling interval for this point is sampling interval is L 1 second, and total data point, the M, is 1000. Okay, a continuous signal is sampled with a 1 second interval between data point. So this meaning this is the sampling interval. Okay, with 1000 samples is analyzed to determine frequency domain resolution. And if total of 1000 data points are sampled, what is the increment size of the signal in the frequency domain? Okay. The frequency domain resolution is 1 over 1000. Okay, 0.001 hertz. Meaning that the frequency components spaced by 0.001 hertz. A higher number of samples improve the resolutions in frequency domain, allowing for more detailed frequency analysis. Lagi banyak kita record will be more detailed, and the data will be the signals will be lagi clear lah. Alright. Okay, what is the maximum frequency expressed by the FT? Okay, this is the frequency spectrum here. Frequency components are represents in spikes. So this is frequency spectrum. Highest frequency components shown corresponds to maximum frequency. Okay, this is Umax, maximum frequency, by following the Nyquist frequency. Okay, Nyquist formula lah. Is okay. Okay, refer to the Nyquist. And then here is on the sampling interval, the distance between adjacent sample point, okay, the delta x. Okay, this is another example. Continuous signal is sampled at 1 second interval, and the 1 second interval, the TS, the sampling period, delta x is equal to 1 second, and 1000 data point collected. Focusing on the maximum frequency components in the transform signal. Okay, so we have the Fs equals to 1 over delta x equals to, we need that 1 over 1 hertz lah. Frequency, sampling frequency. The sampling frequency is 1 hertz. For the F max, it is Fs over 2. So 1 hertz over 2, half or 0.5. Okay. Okay, this is according the decreased frequency. Okay, fundamental of decreased frequency for F max. All right. So next one we go to 2D Fourier transform. To extend the Fourier transform to 2D signals, it is very useful in image processing and widely used in image processing to analyze special frequency content. If we have U and V, this it is 2D, so we need two variables, U and V. Okay, U and V are frequency domain variables. And where is the applications for 2D? Okay, we can apply in image filtering, compressions for JPEG. Normally, JPEG uses discrete cosine transform, a variant of the Fourier transform. Okay, so this is for digital image representation as 2D discrete function here. Okay, each pixel intensity corresponds to a function value of f X, Y. Since it is 2D, so we must have two domain lah. Sorry, two axis. Okay, we have X and Y. X and Y. F, X, Y are all finite and discrete. It is the gray level of each pixel. Okay, similar to 1D, but applied to 2D function for images. Okay, this one for 2D, we can transform from uh, time domain into frequency domain, fxy into fuv. We have two axes. If in time domain, we have x and y. In frequency domain, we have u and v variables. Okay, this is some formulas here. Convert a discrete 2D images into frequency domain representation must carry all the information. From time domain goes to frequency domain or frequency goes to time domain. Used for digital. This one here we use for digital signals and its implementation efficiently using the FFT. FFT is fast Fourier transform. Okay. In the FFT algorithm, speeds up the computations and is widely used in real-time signal processing. So we have two formulas here, FUV in frequency domain, FXY in time domain. To get the FUV from the FXY signal. Okay, to get the FXY signal, we apply the FUV informations, all the informations in the formula here. Okay, application, okay, practical example of a Fourier transform applications in images. Okay, this one is for time domain. Okay, this is for frequency domain. Okay, okay, this is if we have a rectangular function. Okay, and this one is a Fourier transform of the time function. Okay, the refer to this one. The bright horizontal and vertical streaks indicate that most of the frequency content is concentrated along the axis. This one. Okay, and the central bright spots represent the low frequency components, while the spread out patterns corresponds to higher frequency. Okay. As you guys can see here, visualize commonly used in image processing, optic and signal analysis. In medical, apply a lot of these um, signals. Okay. Optic and signal analysis, MRI and CT scan analysis, X-ray. Okay. So if we refer to the time domain, it is hard to visualize. Susah nak do analysis, nak interpret. If we convert into frequency domain, easier to analyze, to interpret. Okay. Uh, FUV, Fourier transform of image, contains all frequency components of the original image as and in fxy. The variables. Value of FUV is complex number obtained from the exponential function from Fourier transform equation. Okay, and general statement can be made where U equals to V equals to 0 corresponds to DC component represent for the average brightness. If for patterns of intensity variations, a different frequency contribute to various parts of the images. Okay, this is another example. If for 2D in time domain, this is not in time domain. Okay, this is the Fourier transform in terms of the analysis of frequency. Okay, more five edges and fine edges and fine textures in image has the more high frequency content in present with the Fourier transform. This is the output sebenarnya. Okay. Okay, this is the MRI scan. The Fourier transform provides a frequency domain representation of an image rather than a pixel by pixel correlation. Okay, MRI scan of human image, and this is the Fourier transform of the MRI scan. As the MRI scanner do not capture images directly but collect frequency domain data. Okay, this is the output yang will display. Okay, MRI scanner do not capture images directly but collect frequency domain data in terms of case-space data using radio frequency signals. Okay, the case-space data transform the images using inverse frequency transform. So we collect, operate, do the analysis, lepas tu baru boleh display. Okay, another one is on the chest X-ray image intensity variations. This is the frequency domain in the FUV lah. Okay. Okay, the bright spot represents low frequency components, smooth intensity variations. Horizontal and vertical bright lines indicate this one here, dominant frequency components along the axis, which contribute to the overall structure of the X-ray images. Okay, this is in the output, okay, in time domain for F, X, Y. Okay, the images has edges, textures, and smooth edges, which can be analyzed in frequency domain. Analysis do in frequency domain. Okay, the output boleh dapatkan in the time domain. Oh, alright. Okay, this is another example. Random images sahaja. Breeze. Okay, this is according on the dominant frequency. It's slightly different here. This is lower resolution. This one with the higher resolution. Oh, okay. So that's all. There is no on the properties because these properties we have covered previously in uh previous tutorial, right, for the properties. Okay, so as for today, we have covered up until the 1D and 2D. Okay, so remember guys, for the final exam, it will cover for all the unit. Unit 1, 2, 3, and 3, 4, and 5. Okay, in Unit 1, we have learned on the concept of signal and system. Okay, what is signals, what is systems, and explain the 7 types of signal classification and nine types of system classification. Okay, and Unit 2, it is continuations of Unit 1. We have two main parts of the unit. We have LTIC, time domain analysis for linear time invariant continuous time, and LTID, okay, discrete time. Okay, and Unit 3, we have the basic concept of system analysis. We have learned on the Laplace transform and also on the inverse Laplace transform and how to use the table. Okay, some of the basic properties lah, we also have learned on the Unit 3. And then Unit 4 is on the Fourier analysis for continuous time signals and Fourier series, Fourier transform, What else? The final unit to bridge the gap between continuous time and discrete time signal as for today. And also on the sampling theorem, we have learned on DTFT, discrete time Fourier transform, DTFT, discrete time fast transform, FFT, okay, and 1D and 2D. Okay. So basically this is the enclosure for the signal and system. Okay. And some of the students ask me about on the final exam past papers. Actually, I don't have the final exam past papers, but you may refer or browse in the past learned. I believe that there are self-learning activities. Okay, some of the question is almost similar and related with the final exam papers. Okay, so you may try, and I think there is also solution in the self-learning activities. Okay, you may try and do the exercise in self-learning activities. And for final exam, if you want to, you may request in the forum discussion with the course coordinator. Okay, might be he wants to share some with you guys. Okay, so that's all from me. Is there any question from you guys? Any question, guys?